Hi, I'm Sebastian Kurfürst, and I'm really happy to talk about highly scalable backend systems. So, just a few words about myself at first. I am a founder of a technology company called Sandstorm. We are currently 30 people. I personally am programming since I think 15 or 14 or something like that, so for a very long time. And I'm also part of an open source project, which is called Neos, which is a content management system, which I like really much. So, about Sandstorm, just a few words. We are 30 people, and actually, this photo has been done on a bar camp where we meet once a year or twice a year for a whole week outside our normal company. Where this photo was taken, we were a bit north of Berlin. And this is where we discuss things, where we figure out how to progress with our company and discuss what to do. And what are we actually doing? Well, we are doing a lot of different projects in different kinds of technologies. And I think this is not really special for any kind of technology company, obvious. So these kind of project companies is like what this focus is. What I think is different is that we're actually having a goal, and we call this goal Sandstorm 2028. So the goal in German ist, wir wollen die harten Nüsse in Projekten mit positivem Einfluss knacken, damit die Welt auch in Zukunft für alle Lebewesen reicht. So in English that means we want to work on the hard problems, on the difficult problems, in projects with a positive impact, such that the world is enough for future generations. So having this goal helps us a lot. It helps us prioritize. It helps us focus on the right things, and it helps us guide us in our daily lives, basically. And we've broken down these values and these goals into specific things. For instance, we have some values, which you see on this slide, and a certain philosophy of working. So we want to create win-win situations with our customers, and we want to work in partnership with our customers. That is really, really important to us. And we have quite a few of them, which you see on this slide. Some bigger ones, some smaller ones, some in the public sector, some in the private sector. It's really a big different, all kinds of things. So let's quickly focus and quickly iterate on the technology side of things. So what are the different areas we are actually doing? So the first section is the first technology branch, I would say, is JavaScript and TypeScript, where we're doing a lot of things, mostly with React and React Native. We have some other projects or some older projects with Ember, for instance, and but most projects in our world are in React and React Native. Then we have the PHP stack, where we do Neos and Flow, where we do Symfony. And then we have the Java and Kotlin stack, where we have Spring usually. And then we have the remaining stack, where we do things in Rust, Go, and C#, for instance. So it's a really different kind of things we are doing in all kinds of different technologies, which is really interesting, which helps us trying to figure out the best tool for the job and also adopt a wide range of our different goals. And the funny thing is actually it doesn't get boring. So I really like it that we have so many different technologies on the place. So we are part of the Neos ecosystem, and specifically we are in Neos core team, and a few members of us are in Neos core team. And for instance, I'm also organizing the Neos conference. I'm one of the organizers there, which happens once a year, where the whole community gathers. And in this year, in 2022, we are actually doing it here in Dresden in April, end of April, in the Alter Schlachthof. If you want to drop by, please just send me a mail and we'll see if we can organize some tickets for you. Especially for students, we have good possibilities for you to get you to such a conference. It is also streamed live and online, so you can also join from your own workplace or from your own living room. But actually being there in person, if that's possible in April, is certainly a good thing, because we can just discuss and meet with lots of people, and that's really nice. Okay, but let's start now with actually our presentation and start with our actual talk topic about highly scalable software. So we are talking about web applications. So let's just quickly iterate some of the basics. Let's just go through of what is actually a web application. On a very high level, it's basically the communication between our users, our clients. Some use an app, some use a browser, and our servers. And these clients communicate by sending requests, and they receive responses. And this process is actually what is being specified by HTTP. So if we talk about scalability, actually, we are talking about the server side of things. It basically means, what if more users use our system? That's the one way of approaching the topic. Or how can more, if the users engage more with our servers, so that if they use the application more, for instance, so that also means that we need to scale, because every user is doing more and more things, and that's what we need to take care of. So the first question we need to answer is, how do we actually measure performance of these kind of request and response-based systems? What can we actually do? And there are two key metrics we need to talk about, which is latency and throughput. And what is latency? Latency is the time it takes from the request until the response. So until from the time the request is sent until the response is received. And latency has some factors which we cannot influence. So for instance, it takes some time for the network packets to travel to our server and back. But what we can influence is the time it takes in our system, inside our server. So that is basically what we try to do there. And the second part is the throughput. There the question is actually, how many requests per time are actually executed? If we look at how these metrics work in detail, actually we are not just talking about latency, because latency is just measured for a single connection. But what is actually interesting for us is the latency distribution. So that means for a whole range of requests, for instance, in the current minute, we want to know what is the average. But the average is not really sensitive to outliers. So for us, actually, it's important. The percentiles are important. So the P95 percentile means what time does it take for 95% of all requests to be faster? And the 99th percentile is the same. So for instance, let's say we have an average response time of 0.3 seconds. Then the 95 percentile is 1.4 seconds. So that means that 95% of all our requests are faster than 1.4 seconds. And the last row means that 99% of our requests are faster than 5 seconds. So you see there's a really long tail distribution, and this is what you see by these distributions and by these latency numbers. And the throughput is actually easier to measure. You just count the number of requests in a certain time frame, like per second is common, or per minute, and then you know that you, for instance, are able to handle 120 requests per second. There's one basic assumption here, which is that we don't do any any error codes in the system. So we assume that every request runs successfully. In a real system, when you have really high load, it might happen that the system does not run reliably. So you would actually need to track the errors as well. So what is actually happening when the number of requests is increasing? So what is our goal? Well, if we talk about that, actually it's pretty easy. In terms of latency, we don't want any changes. We just would like to be our system as fast as possible and as fast as it was before when it was not loaded. And for the throughput, we actually want to be able to handle more people, more requests. So actually we would like our throughput to increase. That is actually what we would like to happen. And for a certain range of time, actually this will work out. But then we have some problems where it doesn't work anymore if the number of requests increase. So we need to zoom into the server, and we have to now discuss what is actually happening inside our servers as the number of requests increases. So our server is consisting of certain so-called resources. So a resource is something like a CPU, a RAM, so the memory, the network bandwidth we have available, and all kinds of different resources comprise our system. And these are limited resources. So that means we don't have unlimited CPU, but we just have two of them. So that means just two things in our computer can run in parallel, or a certain amount of RAM is all we have as memory, or we just have a certain memory, a certain network bandwidth available. And because these resources are limited, what is actually done is that we have a so-called queue in front of the resource, so that if we have more requests for the resource than we actually have it, we park, we handle out parking tickets. Basically, we say, well, you just have to wait a bit until you are actually being handled. And actually, there's not just one queue, but there are many of them. So there's one for the network interface, for instance, there's one for the CPU, and so on and so on. And if now a request comes in and the system is not loaded, the queue is basically empty, and the system and the request can go straight on the CPU, for instance. But if the system is loaded, what is happening is actually this queue is filling up. So if the CPUs, for instance, are really under pressure, so they're really saturated, they are doing a lot of work, then the queues are actually starting to fill and fill and fill. And if that's just for a peak, if it's just for 1 second, for instance, then after this second of high load, the queues can reduce their or they will be lower and lower again, so that is actually will work. But if we have a really high load, then the system can get overloaded, because if the queues are filling up, at some point we need to drop requests. And that is what we call a bottleneck. So a bottleneck is actually a situation where a certain resource is limited, and this resource is not able to catch up to cope with the number of requests anymore. How do we see this bottleneck now in terms of throughput and latency? Well, let's just look at the throughput first. That's the left diagram here. So on the bottom scale, we see how many requests per second are we trying to send. So that is measuring how much load the system has. And on the y-axis, we know how many requests we are able to handle. So for instance, if we try to handle 200 requests, or try to send 200 requests per second, this diagram shows that we were able to handle 200 requests per second as well. So that means all requests being sent were handled in time. So that is the situation we want to have. But now for 400 requests per second, for instance, we are able to handle 350. So that means 50 requests have to be queued or they are delayed. And if that happens for a longer time, then the performance will even decrease in our system because the queues fill up. And if we try to send 600 requests to the system, then actually we are not able to increase the number of requests we are able to handle anymore. And so you see that there's a certain point where the diagram shifts. So in German, I would call this a Kipppunkt, a point where the diagram or where the mechanism becomes unstable. And that's not a linear combination of things. For latency, we see the same. So until a certain point, latency is really flat. This should just the way it be. This should be the way it is. So that basically the queues are all empty, and actually we are just handling everything. We are able to cope with the load. But at a certain point in time, the queues start to fill up, and that's what we see in the latency, because every individual request has to wait longer in some queues, and this is what we see here as well. So what can we do when, for instance, the CPU resources are limited? Well, actually, we can just buy a server which just has more CPUs, and this way we are able to handle the load well. And this idea, this concept is actually called horizontal scaling. It basically means buying bigger servers, but bigger actually means bigger in the sense that we have more of the resource where the bottlenecks actually happening. So that means a bigger server with more CPUs is not useful if your network card is the limit, for instance, or your disk is the limit. So that means you always have to measure and you have to know what actually your limit is so that you're able to handle that and to fix that problem. So if we have horizontal scaling, we as well have vertical scaling. So that means having more servers, more of the same servers, and somehow distributing the load. And the remaining talk will be about how we can handle this distribution of load amongst different servers, because it's not just adding new servers and that's basically it, but actually it's way more complex than it, as we just see in a bit. I would just like to point out that horizontal scaling is usually a very good idea to do. So that means if you can solve your problem by just adding or buying a bigger server, then that's probably a good idea to do at first. And as soon as you reach certain limits there, or you want to be able to tolerate failures in terms of that a certain server is offline, then you need to scale vertically. But as you will actually be able to come a long way just with horizontal scaling at first. Okay, but back to vertical scaling. How does it actually look like? So we want to add more servers to our system. So let's just look how this would actually work. We have our three servers, our three users, and who can send requests. And we have now not just one server, but two. Now we need to talk about how is actually the request dispatched from the user to the server. How is that actually done? And you might know that this is being done usually by a system called DNS, domain name servers. And the domain name service resolves IP addresses from names. So that means we have a name like api.sandstorm.de, for instance, and that resolves to a certain IP address. And what we can now do in DNS is actually for one name, we can specify multiple IP addresses like it's done here. So here we basically say api.sandstorm.de should go to the .14 address and to the .15 address. And what our clients are now doing is they randomly choose one of these lines for their requests. And they do that just randomly, basically for every request, they decide which one to take. So let's just imagine one server goes down. Are we finished now? That's the question. If one server goes down, then some of the users' requests will fail. So in this case, the red request will fail. There will be no retries or anything like that, but it will just lead to a failed request. And that is the main problem, because if we have two servers and one server is down, then actually half of our requests will fail. And now let's just imagine for a second that that half of our requests are failing. Is that meaning that half of our users don't get service, or is that meaning something worse? And the problem is, if you imagine a normal web application, a normal website, for instance, we don't just do one request and we get everything. But what we are doing actually for a website is we are doing multiple requests, one after the other, to fetch all kinds of resources, to fetch images, to fetch CSS, to fetch all kinds of things. So the problem now is that of all these requests, about half of them will fail. That means that we don't just have the situation that if one of our two servers is gone, that half of our users will get bad service, but actually we are getting the problem that all of our servers will get somehow a broken state. Some users will, for instance, get some images, which others don't. Some users will get the CSS or retrieve the CSS, but others don't. And it will lead to all kinds of chaotic problems. And that is basically what our problem here is. So that means DNS is generally able to do some kind of load balancing, but as soon as m servers fall down and we have n servers in total, then m divided by n requests will fail. And now comes the point. This basically means the system is unavailable for all our users. And that is the dramatic problem, that basically it's not just for a few of them, but for all of them, it's not they are not possible. We are not able to do any kind of service. And that is the main problem we are having. Right. So that means DNS is probably not the answer. So let's think about what we can do. You have probably heard of a system called a load balancer. So let's try that. If we use a load balancer, our APIs look like this. So in our data center, that's the box on the top, we basically now have our two servers and we have an extra load balancer in front of it. And the load balancer is what the name is doing what the name is saying. So that means it receives all the requests and it will delegate it to all the servers. It is also sometimes called a reverse proxy. That can be the same thing. And basically, the load balancers are trying to figure out what servers are online and what are not, and then send the requests only to the online servers. So that means that load balancers enable data security, or they enable failure resistancy and a high performance. But now the question is, what happens if the load balancer fails? Because that would be also a single point of failure. And I will just skim that really roughly because that is a topic on its own. But basically what you are doing is you use two of these load balancers, and these two load balancers should monitor each other for availability. And what you then usually do is you have a so-called virtual IP. That means an IP address which can float between both load balancers. You can do that, for instance, via ARP protocol. That's the way that can be done. And what is now happening is that you have one load balancer which is active, and the second one is just on a standby mode. And now when this one load balancer gets down, the second one will figure that out after a few seconds, and then it will take all the IP addresses from the other node and take this central IP address from the other node, and this way provide service. But you see, that is already quite in itself quite an endeavor, and it's quite complex, so it's not an easy thing to do. If you want to know more about that, there's a project called HA Proxy, so High Availability Proxy, which is an open source project, and you can build load balancers for these kind of things with HA Proxy. So if you want to know more about that, that would be a good option. Right. So let's just say we have one load balancer, and that's enough for us, and we have two servers. If one server contains information for a certain amount of for a certain user, for instance, and we now have two servers, the question is, how do I know where I find which data? So let's say this first server is aware of all the usernames from A to M, and the second one from N to Z. And now suddenly the load balancer needs to know, oh, well, I need to send the requests to the left or to the right side. And that is really, really complex. So that is not a good idea actually to do. So basically the load balancer has no clue which servers to ask for a certain data set to have this available. And what can we do about that? Well, if we zoom into a server, basically it is consisting very roughly it has two parts. It has a data part and it has a logic part. And the data part is called stateful. It contains state. And the logic part is usually stateless. So that means it does not contain any state, but it just works with the data. And what we can now do is we can actually tier the stateful part away from the main servers, and we basically move the stateful part into a separate layer of our distributed application. The goal of that is to be able to scale every part individually. And now let's quickly go through the different parts of the state, what they would actually mean. So we have databases. Databases are stuff like MySQL and Postgres, or we will talk about them a bit. They are usually having the main store of all the data in the system in many applications. The second thing we have is a so-called session store. Sessions are is temporary information we need to store for a certain user. So for instance, stuff like the login state. If we have a web shop, we want to remember what is in the user's basket, for instance, or is the user actually logged in or not. And this is information which is usually stored in a session. How do these sessions work? Well, basically they are you have a user has a so-called session ID, and this is what the user has inside a cookie, and this is sent on every request. And on the server side, for this random session ID, actually a bucket of information, a serialized bucket of information, is stored. And the third thing actually we might have are files. So think about big files like images, videos, audio files. That's also what we need to take care of, because databases are not really good at storing these large binary data things. So by moving our state out of the stateless logic out of the server, actually we now have 4 parts which we can scale independently. And that is the main benefit of that we are now able to scale the servers with the business logic and the database and the sessions and the files one by one, depending on their needs, depending on where actually the bottleneck exists. And this is actually also our plan now for the next for the upcoming minutes, and for probably the next half an hour. We'll actually go through every component individually, and we'll discuss how to scale the server, how to scale the database, how to scale the sessions, and how to scale the files storage, and how to make that highly available. So let's talk about the server first. How are we scaling servers? A few years ago, actually, what we had was a so-called traditional deployment. We had a certain hardware with an operating system on top, and on this physical hardware, we deployed multiple apps. And this led to some kinds of problems because, for instance, one application needed a newer Java version or a newer PHP version than the other, but these versions of libraries were installed globally, so you had a problem and you had to really watch out that this is consistent. As well, updates were a big problem because for updating you needed to always, if you updated, for instance, also the Java version, you somehow needed to install a completely new server from scratch. You would need to go to the data center and provision new hardware, then install on the new hardware, install a new system, and that was really hard just for testing something out, for instance. What you also had was that the apps within each other had all kinds of problems. So for instance, if one application was very resource intense, it had the potential to tear down the other applications. These were the problems of the traditional deployment model. That's why at some point virtualization happened. So that was the idea that you could buy virtual machines instead of physical ones from your providers. So how does that work? Basically, you have the hardware and an operating system on top, and then a so-called hypervisor. And the hypervisor is able to start virtual machines. This is so popular hypervisors are, for instance, Xen or KVM or VMware as a commercial one. And actually, each virtual machine has an own operating system, and then inside the applications, and you have a very strong boundaries between these virtual machines. So actually they don't see each other, and it's very hard for them to influence each other. This is made performant by some processor extensions which are around since quite some years. But actually this is how this really took off, because Intel and AMD supported these processor extensions since a very long time, and this made virtualization actually quite fast. But still, now we don't just have one operating system which we have to patch, but suddenly we have 3 of them. We have the main one and one for every container in the example here. So that is just more work to do. And one thing we are seeing since, let's say, 3 or 4 or 5 years more and more intensely is a so-called container-based deployment. This is basically that this is enabled through some Linux kernel features named C groups and namespaces. and this enables some separation between, or very strong separation between processes, but still they share the same kernel. And this leads to a less big stack. So basically you have a hardware operating system, then a so-called container runtime like Docker, that's the most prominent one. And then inside each container, you just have binaries and libraries and your application, but you don't have a new kernel, for instance. So it leads to a somehow slimmer stack. It leads to the fact that the containers are able to start way, way quicker than virtual machines. It is having a lot less attack vectors because the containers are smaller, and that's generally a really helpful thing. So that means what you usually do is you package your applications as Docker containers today, and then you need a way to run these across a fleet of clusters. And the most common way of doing that today is actually using Kubernetes for this kind of scalability. Another one would be a HashiCorp Nomad, which is which is also really good, but which is more simple. It's not as involved as Kubernetes. So basically, this container deployment is state of the art, I would say. So this is basically how things are done today. The problem is actually that containers in itself are quite complicated. So this is actually an image of the Kubernetes documentation, which explains the different parts of the ecosystem you have available and which need to interact with each other for providing a system. So you have a control plane, you have storage, highly available storage, and you have the different nodes with all kinds of daemons which need to work with each other to give you this one big cluster. So actually, Kubernetes is a really, really good tool, and I can very much recommend that, but it only is useful starting at a certain scale. And it definitely has a learning curve. For the complexity Kubernetes has, actually it is running really, really smoothly once you have it installed. And luckily, there are some projects which make installation quite easy. So that means there are different Kubernetes so-called distributions on the market, which are also open source, pretty much like Linux distributions. And they are different in the way they are installing Kubernetes and in details how you run them. But internally, as soon as you have a standard Kubernetes, actually, you can use any of these distributions. And the quickest way to get to to running Kubernetes instance is probably first is going to a cloud provider. That's the one way of doing things. So you could just go to AWS or Google Cloud, and then you can click some buttons in the UI, and this way you can get a Kubernetes instance. Or if you want to run it on your own servers, there's a system called K3S. So K, then the number 3, and then S for servers. And K3S.io, that is what we are, for instance, running in our clusters. And this is what I can recommend really a lot. And this way you can actually set up Kubernetes with just 3 or 4 steps. And that is quite simple. And it's even possible to set up a highly available Kubernetes like this with a bit more setup, but still that is very recommended. So one could think that actually we have our problem solved now. We're actually finished. We can scale out our servers. So is that actually everything we need? Well, it turns out no. When we are able to scale out the servers, actually we can scale to quite some many requests. But we still have to take care of the database, the sessions, and the files for that to work out well. It's really common that if you measure the different times in your system, then actually quite some time is spent in the logic of the server. So that means what is a common scale, for instance, to have 5 or 10 server instances running, but still just one central database or one central session cache or one central file storage. So that means you can have actually quite some, you can reach quite a big amount of scalability by pulling out the layers and then by being able to scale the server in a system like Nomad or Kubernetes. So that is actually a really good idea. Okay, but let's now talk about how we actually can scale the databases, because that's the next topic. if we look at databases, actually there are open source ones like MySQL and Postgres are probably the most common ones in the SQL world. And then there's also there are no SQL databases like MongoDB or Elasticsearch or CouchDB, which work in a different paradigm, which basically don't have SQL as the language. Just quickly, if you are in doubt which one to choose and you don't have any preference, then I would suggest to choose PostgreSQL, because it's a very powerful database. It has lots of features. It is enabled. It's developed in a really good fashion, and it's well maintained. It's an open source project, and so it's free to use for anybody. And it is very, very advanced and can provide you a long way further. So let's just say we want to scale out Postgres. We want to have a distributed database. That is what we could actually do. We could try to run this system called Postgres, the database, on multiple machines, but it should still give us the illusion that it just is all running like a really big machine, which is basically never going down. And there are solutions to that, like CitusDB, for instance. That's also that's a way to run Postgres highly available. Or MongoDB, for instance, can run highly available right out of the box. And this diagram on the left is actually from the CitusDB data, just a high-level overview diagram, how the different parts of a distributed Postgres interact with each other. And what you probably see is actually, just by looking at the boxes, that it's quite complex. It's quite a lot of different pieces which need to fit together for a highly available Postgres to actually work out. So that is definitely something you won't do lightly, and it probably also doesn't support all kinds of database features. If you use a NoSQL database like MongoDB, things might be a little bit easier, because usually what these databases are doing, like NoSQL databases are doing, like MongoDB, they are trading some consistency for more scalability. So that means scaling out is easier and scaling to multiple servers is easier, but you lose a lot of guarantees like transaction isolation and these kind of things, what SQL databases give you for granted. Right, so distributing the database is one way of doing things. What is the second idea what we could actually do? We could say we are splitting our data into different kinds of databases. So let's say we have two databases in our application, and the first database is around and has to take care for all the users from A to M, and the second one from N to Z, for instance. And now, all the time the application wants to load a user, actually it checks the username and then it goes to the left side or to the right side. This system is having less complexity on the infrastructure side, so actually it's quite a good one to run. But it's more complex in the application, because suddenly in the application you now have to handle two database connections instead of one. And the problem now is, if you imagine that there are cross connections between the data spanning multiple databases, then things get really interesting and really difficult. So that is something which is problematic here. And also what is difficult is rebalancing that. So what do I mean by that? Well, it might be that there are more users A to M than N to Z, for instance. So that means that there's more load on the left system than on the right system, for instance. And it's difficult to balance that out, because if we have made this rule A to M and N to Z, it's actually hard to change this rule. So imagine you would like to add a third database server now. Things will be really difficult, because you somehow need to migrate some users from DB1 to DB3. You have to migrate some users from DB2 to DB3. And you have to let the application know when this migration is completed and what the migration state actually is. That is quite a lot of work. To mitigate that, there are actually two strategies. The first is we usually don't use the user's name, for instance, for sharding directly, but we hash the user's name. And a good hash function has a very even distribution among the whole key space. And this way we are able to really send half of the requests to the left side and half of the requests to the right side. Although it's not anymore possible to decide just by looking at the user's name which one to choose, because you actually have to hash it beforehand. And the second idea is what is called a sharding key. What you usually do is you basically pack your data together into some intermediate units. So not every user individually, but basically you would say something like we have 50 boxes or where we place our users in. And now we say at starting, okay, the first 25 boxes are on the left server and the second 25 boxes on the right server. And what you can now do more easily is actually move one box at a time to a third server and then update the information that this box was actually moved. And this is called a sharding idea and sharding key, this kind of intermediate layer where we can move things around then more easily. And it depends very much on the kind of application, if this is a sensible way to do. So for instance, if you are doing a social network, it's very hard to do this kind of thing because you will have all kinds of cross-references between your users, for instance. Where this idea works really well if you have a multi-tenant system. So that means if you have a system for multiple clients, which basically all have a really separated instance of each other, there this would fit really well because you would then just all the data of a tenant has no cross references to any other tenant, so you are basically free to move this data around as you see it fitting. So that is a very a good thing to use for this kind of approach. Right, so what we've seen right now is two approaches. We have seen like one really big scalable database, so spanning multiple nodes. The second idea was sharding the application, the data in the application. And it turns out actually there's a third idea, and that is actually not scaling at all. And that sounds funny first, right? Because you think, well, how can you not scale? Because actually you know now your database is the limit, so you have to scale somehow. Well, the idea is to use a cache layer before the database and to reduce the amount of traffic or the time it takes for the database to answer this load. So you actually look a bit closer, how is this load generated? And what you can do is you can do caching. So that means instead of asking the database the same question again and again, you actually cache the result in a distributed cache. What you can also do is you can analyze your queries, and then you can add more database indices. And actually, that is a really huge factor. So that is very useful to do as soon as you have a performance problem. Looking at the slowest database queries and the ones which take the longest time, and then improve that by adding database indices is a very good idea. And what you can also do sometimes is you can put more work into your application logic so that you don't have to ask the database so often again and again. So that can be also a sensible way of doing things. So actually, this not scaling is actually a very common way of doing things before trying out the other two ways. I would say it's the most common one actually, and the most useful one to first look at caching, look at the database indices, and to look whether we can improve or remove the load problem by thinking about more clever application logic. Right. So let's now not talk just about the database, but let's go to the session and the caching layer, because that is a good step over. So if we say we have a database and we want to cache information, this cache needs to live somewhere. And one way of caching would be to place the cache in every individual server. But the problem is actually not the caching itself, but the cache invalidation. So that means how do we remove the cache entry when the data has changed? So somebody famous, I don't remember said, well, there are only so actually cache invalidation is a really hard problem in computer science, right? So how do we handle caches and session in a highly scalable system? Well, it's interesting because the solution is almost always called Redis. Redis is a highly performant caching system. It's an open source project as well. And it's called, or they call themselves, a data structure server. So that means it can be a cache just by having a key and store some value for that. But it also supports lists, it supports maps. You can script that via Lua, which is a small scripting language. It is quite scalable, and it has some fancy things like probabilistic data structures for counting high cardinality values, for instance. So, and the interesting thing is that like Redis is really unique. For databases, for instance, you have multiple databases on the market, a lot of them. And you have commercial ones and open source ones and these kind of things. For caching and sessions, like for caching, you also have multiple products on the market. But interestingly, for the feature set which Redis provides, so not just simple key value caching, but for this more of things, actually everybody uses Redis. So that is a really funny thing, that like everybody in the industry, no matter if it's a really small company or a really huge mega corporation, they are all using Redis in all kinds of places because it's so flexible, it's so easy to run, and you can reach high scalability with that. There is one catch to it, which is that all your information, all your data you store in Redis has to fit in memory, because that is how Redis is so fast, is by making the data available in memory directly and then directly accessing that. So if you have some minutes to spare, I can really recommend you to go to the Redis website, read a bit, try it out a bit, and it's a really good project, which is, I think, very much underused in many projects, actually. Right. Now we've seen about how to scale the server with Docker and Kubernetes, how to scale databases, how to scale session and caching. And now we'll check out how we can actually scale files. So let's look at storage. Actually, there are two main kinds of storage solutions on the market. The first one is called network file system. It is basically the idea that you have just a normal file system in the cloud, so to speak. So that means you want to have a file system which does not live on your server, but which lives in some more servers. And actually, your file system at first glance is really easy. You just can store files and directories and so on, right? Well, it turns out it's not so easy. A file system today on Linux is called POSIX compatible, and that means it provides lots of features you might probably never heard of, and I have never heard of. So stuff like locking, for instance, and really specific guarantees when data is written, when it can be read back, for instance. And these kind of guarantees don't matter to you as an application developer usually, but they matter if you, for instance, program a database. Then it's extremely relevant to know when your data is actually stored to the system and stored on the files, and when it's persistently done. So that means actually implementing or this POSIX compatible file system which NFS provides has a huge API. It's really big. And because of that, it's actually really hard to scale because of this big API surface. On the other hand, you are having so-called object storage, and the most prominent one is actually called AWS S3. So from Amazon Web Services, a system called S3. That's a commercial one, and they actually created this kind of space by providing S3 many years ago. That was the first AWS service they have made publicly available. And the idea of that is actually that you have an HTTP API, so a REST API to communicate, and you can put new data in there, you can read data back, but it is this API is way, way smaller than the normal POSIX API, so you cannot do locking, for instance. And it is quite easily scalable, but your application needs to support it, because your application now needs to talk with the S3 API via HTTP and not just via placing files on the file system. And that would be a bit bad if S3 would be the only option. Then this would mean actually you would not need to go to AWS for your services. That's not what we are doing, for instance. What is happening is actually that many providers give you an S3 compatible API. So Google does that, for instance, or DigitalOcean is doing that. And there are two good open source three good open source implementations you can also run. So MinIO is probably the easiest one to get started with. Actually, that is an open source implementation for implementing the same API, which you can fully run on your own servers. Then the second one is called Seaweed FS, that is providing a distributed file system, also among other options having the S3 API. And also Ceph, which is a big system, a big open source system for distributed filing. Actually, this is also having an S3 API. And if in doubt, actually, I would start my applications today such that they support this kind of object storage. And what you need to take care is that you don't just place files on a disk and read them back, but that you actually have a separate layer in your application to store persistent things. And the easiest implementation is just storing that on the file system then, but you're able, by having this application layer for storing resources like files, actually you are able to swap in and out these components later on. So our projects usually use a normal local file system, but not directly, but through this abstraction layer. And then when the project needs to scale out bigger, actually what we are doing is we are replacing this file system, the local file system, with an S3 compatible system. Right. That was quite a ride, I would say. We've now talked about how to make a server scalable. We've talked about a load balancer. We've talked about the servers, the application servers, scaling with Docker and Kubernetes. We've talked about how to scale a database. Remember, the one way was not scaling. The second one was to use something like C2SDB, a distributed database which can run on multiple systems. And the other option was sharding inside your application. We had sessions and caches with Redis, and we now had files with NFS and the S3 compatible object storage APIs. And you see there are quite some different lines here and different boxes which correspond to different computers usually. So running that is actually, it's not easy. You need quite a good monitoring, you need good alerting. Your systems need to or you need to gain operational expertise, how to run that and how to handle failures. So it's quite some work. And to illustrate that, I would like to conclude this presentation with one part, which is basically what can possibly go wrong. So that's actually a part, that's a real world application which has gone wrong, where some errors have occurred. And I think that's a good example of like real world error scenarios which can break such a system. Right. So what do we have here? We are having a central database in our system that's actually on a production system of one of our clients. We have a few servers for the application logic, and we had a load balancer in front. And in our case, the database was actually a Redis system, because Redis can also run in some kind of persistent mode, and that is what we have been doing here. And what has now happened is that I have been developing a feature locally on my machine, and locally I also had my Redis and my logic, and I tested this thing, and then I didn't see any change. I was totally stunned. I was like, I modified something. Why am I not seeing my result? And then I thought, well, that's that's weird. Let's just enter some really bad value into the database. And I did that, and then I refreshed my page, and still the value was, nothing changed at all. And I was like, oh, that's weird. And then I remembered, oh, I still have an SSH connection open to my production database right now. And what I've actually been doing is I have changed the production error value here. So I've entered definitely an error value into this database. And this error value led to the fact that the servers returned a fatal error. And because that is a central point in the database, actually, what has happened is that all the servers have returned a fatal error. And on these systems, what we actually have been doing is a so-called kill switch on the server. So that means there's some detection logic checking whether the server thinks itself it's healthy or not. And if it says, well, I'm currently unhealthy, I'm currently doing weird things, then I'll just kill myself. I'll just ensure that I am not able to handle any HTTP traffic anymore. And by doing that, the load balancer will detect that, and this way the load balancer will not direct traffic to the server anymore. Yeah, and guess what happened? Actually, this didn't just happen on the first server, but it happened on all servers. The load balancer removed the failing servers, and this way the page was down. And I've explained that now over the course of a few minutes, but actually what happened was this whole process took probably 5 seconds from start to end. So from entering my wrong value, to actually the load balancer deciding to only return full errors, this probably took 5 seconds for the whole system. And in the monitoring, actually what we saw was that. And so we saw a really big spike of errors, and then we just saw nothing. We were not able to handle any requests at all. And it took like 5 to 10 minutes to boot everything up again to a consistent state, so that the system started to normalize again. So you see, these systems are really, really fast, and also I saw the error like 10 seconds after I made it, but that was way too slow for being able to correct anything of that. And our normal intuition usually thinks or we are usually thinking in our own time. So it's very hard to imagine how a system will behave, which is just so much faster than we do. If such a thing happens, it is really important to do a so-called post-mortem. So that means to think about what we can do to not just fix the error, but prevent this error from happening. So basically learning from the error and trying to prevent it the next time. And so, for instance, what we have been doing there is in the output of my console, I've added these big red lines, and these say production. And on the testing system, it says staging, and it's yellow, and on the development side, it's just green, and there's really small green indicator. And this is the idea that you really see in your face, oh wait, you have a production connection open right now, and this way I would not have added some weird data to my system, because I would have recognized, oh, I'm still on production. So that is something what we have learned from this incident, for instance, among other things. Right, and then we have I've another error scenario which is really difficult, which goes into the topic of it's not always how it's supposed to be, and that's a bit hard to explain, but I'll try nevertheless. So what we had there is actually we had a central server which consisted of 2 Redis instances, one for the sessions for the cache data for the sessions, and one for our cache data structures in our system. So these were 2 separate Redis systems, but they were on the same machine. And the cache system had a specialty because it was just handling the normal requests, but when the user did something, when an editor did something to the site, actually we had a huge peak of these requests on the cache, and then we again had a flat list there. And what we have seen in our system is that this all the time when this peak happened, there were errors in the system on the front face. So actually, we saw this peak going up, and then we saw a front-facing system with all kinds of errors for like a minute, and then the system stabilized again. And we were wondering, well, we didn't deploy anything, we didn't change anything. What is actually going wrong now? And what we figured out after a while, and it took quite a bit because it was hard to track down, was the following. It turned out there was a bug in the application which led to massively increased session state. So that means the session state we stored for every individual user was probably 5 kilobytes beforehand, and after the change it was 500 kilobytes. So you see that's a dramatic increase. And because of that, the system had to transfer more data with the session state. So we had more and more data coming out and into the session database. And this in turn led to the fact that the other data for the caching system actually was buffered longer in the network stack. So we have seen that the network stack was fully saturated. So that means we had a gigabit connection between our servers, and this was completely full during these peak times because the error with the sessions led to the fact that the network traffic was already like 3/4 full or something like that. And then the peak led to this tipping point and exactly led to the situation where it still ran somehow through, changed to, oh, we have no chance of running anymore. And this kind of peaking happened, this kind of nonlinear behavior happened. And it was actually really hard to track down because we always looked at the wrong place. We first always looked at this caching system because we thought, well, this must be the culprit. But actually, the main problem was actually on the session side of things, and the sizing there was the main problem. And as soon as we figured out that actually the network bandwidth was going to the limit, then we also understood that this was the way these different modules interact with each other. Then we had a really plausible explanation what has happened there. But as said, this had taken quite some hours and some days to figure out, and some really slow thinking. So that's what I can really recommend for that. But it's really interesting. I really, all the time when you had this kind of problems, actually afterwards, it's really interesting because you could learn so much from that. Although in the moment, it's of course stressful because you want to solve the problem as fast as possible. Right. So let's end up with a summary. So what did we do today? First, we talked about scalability, and we introduced what this actually means, and we talked about latency and throughput. We then talked about how latency or how limits happen, or how bottlenecks occur in a certain system as soon as a resource is saturated. And we talked about this nonlinear behavior, so that this happens at a certain tipping point. Afterwards, we talked about horizontal scaling, which is adding more servers, and vertical scaling, which is about horizontal scaling, about adding more resources to a certain system. And then we talked about vertical scaling, which is about adding more and more servers. And then we talked a lot about this vertical scaling, where we discussed very many ways of doing that. And remember this diagram where we said, okay, we need to scale the load balancer, or we need a load balancer, we need to scale the stateless servers. And this is what we discussed with Kubernetes and Docker. We have to scale the database with the different approaches we have seen. And remember that also not scaling the database, but going a different route might be a good option. We talked about sessions and caches via Redis. And we talked about files using the object storage APIs around. And we concluded the whole thing with some tales from practice, basically explaining what can go wrong if you have such a complex system. So that's it from my side. Thank you very much for watching. I would be really interested in some feedback. And if you have any questions, just write me an email, or I would be really glad to hear from you. So thank you so much. Stay healthy, and bye-bye.